chemical reactions. And the way I classify them is by, I don't know what to say. Let me just leave it like that. My first classification is just types of reaction. The other one, I'll figure out the name, okay, for it too. But in any case, the types of reactions that you have, there are typically 4 types of reactions that we talk about. The first one is what we call synthesis. A synthesis reaction is also called combination. And a combination reaction is where you're trying to combine 2 things together. Okay, so the first reaction I wrote out for you, carbon plus oxygen to give carbon dioxide. This is a combination reaction. It's also called a synthesis reaction because you're trying to make something, okay, in there. So that's a synthesis reaction. Usually for a synthesis reaction, you will have a lot more chemicals on the left-hand side and less on the right-hand side. Okay, less meaning not atomic-wise or weight-wise, but the numbers that you have in there. Okay, so there are 2 chemicals here and only 1 over here. So that's synthesis. Second reaction that you can have is what we call a single displacement. Single displacement. Displacing means that you're trying to get rid of something or displacing something else. And we've done this reaction also. This was hydrochloric acid and zinc. Wrote this reaction out for you last week. And this was zinc chloride and H2. And as you keep going with more and more chemistry, then things will hopefully start bothering you if they are not right. Yeah. And hopefully it's bothering you now. Is it bothering you? What is it, Samara?
It should be HCl.
You want it to be 2HCl?
Yeah.
Okay, good, yeah. And that's the itch that you need to scratch, okay? And just scratch it, okay? Because it's nice. It's good to know that your equations are balanced, all right? So this is what we call a single displacement. How is it a single displacement? Here is a single chemical, which is zinc existing by itself. And in this reaction, it displaced hydrogen, okay? And so then hydrogen is by itself now, and zinc is combined with chlorine over here. Okay, so this is a single displacement. The third one is what we call a double displacement. I've written, I think, almost all these reactions for you, one way or another. It's just not putting it in context. So here, if you have H2SO4 plus sodium hydroxide, sulfuric acid plus sodium hydroxide to give you sodium sulfate and water. And again, yes, if you want to go ahead and scratch the itch, you can go ahead and do that. 2NaOH, and then I think it should be 2H2O. That will balance the equation. In a single displacement, you were displacing only a single chemical, which means that an element existed by itself. In case of double displacement, there are 2 things that are getting exchanged. Okay, so here, sodium is combining with the sulfate. Okay, so 2 things are displacing here. So once sodium here is combining with the sulfate, then the H2 is now combining with the OH, okay, to give you the H2O. And then lastly is decomposition. And as the name says, decomposition, it means you're decomposing something, which means you're going to start with one thing, end up with more than one thing. Classic example of this one is this example here with potassium chlorate, KClO3 to give us KCl plus O2. And yes, we can go ahead and balance the equation. 2, 2. So in case of decomposition, you start with one chemical, you end up getting more than one in the product. Okay? This is a very basic fundamental classification. Almost all reactions can be classified in one of these categories. okay? Whether it's a single displacement, double displacement, whichever type it is, you will be encountering all kinds, okay? And especially in this chapter, you will encounter all of these kinds of reactions, and you will have to classify them one way or another. At least you should be able to identify it, okay? All right, so this is one type of classification of reaction. The second type of classification is chemical classification, as you may want to call it, I don't know. And in the chemical classification of reaction, we have three different kinds of reaction. One is called precipitation reactions. Precipitate is something, a solid that forms. So for example, if I take silver nitrate, add sodium chloride to this, I will get silver chloride and sodium nitrate. When we start doing chemical classifications of reactions, then it's really important that we also start writing our state functions, okay, in there, the functions, whether it's a solid, liquid, gas. And in this case particularly, these are all aqueous. AgCl, however, is a solid, and then sodium nitrate is aqueous. Which means three things are soluble in water. One of them is not soluble in water, and that's the precipitate that's forming, okay? Looking at this reaction right now, the precipitation reaction, which one would you classify it as? Synthesis, single, double, decomposition? Double displacement. Very good. Okay, so precipitation reactions generally are double displacement reactions. If you want to write that little note for yourself, you're most welcome to. Okay, because it's nice to know that these are double displacements. Okay, the second type of reactions are considered to be neutralization reactions. These are also called acid-base reactions. And I will write a different one here for you. There's already one on the board, but still. Again, since this is a chemical classification, I'll have to specify whether something is aqueous or liquid or whatever. So here we go. This is aqueous. KOH is also aqueous. And then KCl, potassium chloride, is aqueous, and then water is a liquid. Water is by itself not aqueous. If something is dissolved in water, it's considered to be aqueous, but when water is by itself, it's considered to be a liquid. Okay? All right. How would you classify this one? 1 second. Which classification would you put that in? Single, double, also. This is also double displacement. Okay? All right. Oh, what's your question, Samara?
Do you just know that they're aqueous because, like, that's how you know? Like, if
right
we were
now,
given
that's how we.
question,
Yeah, that's how we know. And eventually, as we learn the chapter more, you will know. Also.
Okay.
Yeah.
So just as you learn what
Yeah.
each chemical
Yes.
or what
Yeah.
reaction is. So like,
I'm already getting a little ahead of myself over here because I want to do the classification first so that when I get there, it'll be a little easier for you. Okay? Yeah, but I am a little bit ahead, but you're right. Okay? You will know whether something is aqueous either by reading the problem, okay, or by learning the properties, which we are going to. Yeah. Okay. The neutralization reaction, by the way, neutralization means acid-base reaction, and from chapter 2, you should know your acids and bases. Okay? So hydrochloric acid, which is always aqueous, right? Acids are always going to be aqueous. Bases may not need to be aqueous. Okay? Can you identify one other reaction on the board that is acid-base? Number 2. I see the acid there. I don't see the base there. At least thanks for not saying 1. Yeah. Number 3. Sulfuric acid and sodium hydroxide. Acid, base, okay? Thus I was asking you whether this is double displacement. Hopefully if you said double displacement, you would look for double displacement there. But you didn't do that. You should have done that. Okay? Yeah. All right. Make the connections. Okay, so neutralization reaction. So that's also acid-base reaction, and that's why I took a different example. So you'll at least have two acid-base equations here with you. The third one is called oxidation reduction reaction. These are also called redox for short. And redox reactions are a little bit weird, okay, because they can be any kind, okay. A lot of the oxidation reduction reactions are actually the first two kinds there, the synthesis, the single displacement, and sometimes even decomposition. So those three are actually going to be your redox reaction, so it's a lot. I'll just do this one over here, HCl plus zinc to give zinc chloride and H2, so 2 here. HCl is aqueous, zinc is a solid, zinc chloride is aqueous, and hydrogen is a gas. And again, write a little note for yourself somewhere that oxidation reduction reactions are primarily synthesis and single displacement reactions, okay, and some of the decomposition ones. Yes?
If you're given like two compounds, it's pretty much always going to be a double displacement or a decomposition, correct?
If you're given two compounds, it could be synthesis also.
Okay.
Okay, yeah. So you have to look at the totality of the reaction, okay, not just one thing, yeah. So those are the two different kinds of classifications for chemical reactions that you can have. Now let's talk a little bit about aqueous systems. Okay, then. All right, aqueous. What does aqueous mean? It means when something is dissolved in water. There's one thing that you have to be really careful of, okay, when you talk about aqueous things. When you take sodium chloride and you add water to it, the sodium chloride disappears, right? And you've done that in your separation lab also. So when that sodium chloride disappears, you have to think about the process that is happening in there, okay? What would you call that process? It's dissolving in there, okay? A lot of times I hear people saying it turned into a liquid. Did it turn into a liquid? No, because that would actually be liquid sodium chloride, correct? Going from solid state to a liquid state. So solid to liquid state meaning that you have to provide energy, okay? Just like you have to provide energy to boil something, okay? So even to go from solid to liquid, you have to provide energy, but that didn't happen. You could do that at room temperature, okay? Although some things do require water to be soluble, but still, okay? So the process here is really important that you understand that when sodium chloride is going from solid state into a water state with water, then it's actually dissolving in there, okay? And so which means that if you have NaCl as a solid and you add water to it, it becomes NaCl aqueous. The water is just there. The water doesn't do any reaction. And then what happened? At the end of the reaction, at the end of the lab, what did you do? You evaporated the water off, right? And you got the sodium chloride back. And you know that also it was a physical process then, because you didn't lose your sodium chloride and you didn't lose the water. Well, you lost the water, but only because you didn't collect it. Okay, you could have easily collected it also, all right? So here, if you add water, you get this. If you subtract water, you get the solid back. So it's a physical process, okay, that you're doing over here. So my concern is right here. Okay, right here when you have sodium chloride going into sodium chloride aqueous, okay? Sodium chloride, would you consider that as an ionic compound or a covalent compound? Ionic compound, okay, because it's made of a metal and a non-metal. By the way, that is your first task in this chapter, to figure out if a compound is ionic or not, which is so chapter 2 now, okay, that you should already know this. So If you have an ionic compound, which is a metal and a non-metal, then it's going to be ionic. Okay, and if it's ionic, then this is what happens to it in water. As soon as you add water to it, okay, as soon as you add water to it, it dissociates to give you two ions. Okay, and this is aqueous, and now this is also aqueous, and these ions are dissociated in water.
So salt water isn't just like salt floating around in water, it's actually like
Ions.
sodium floating around in water. And
No,
chlorine.
sodium ions dissolved in the water.
Okay.
Yeah, not sodium. You can't say sodium because sodium itself is a metal. Okay, so not sodium, and it's, yeah, so it's important we say sodium ions, and here we'll say either chlorine ions, but nobody says chlorine ions. You call it chloride. Okay, and that's why I gave you that nomenclature sheet also to make sure that you understand the difference between ions and compounds, okay, themselves. So you have these two ions down here, okay? What about the water? Where is the water? Between them, everywhere, okay? So the water is actually all around them. So when nothing happens to the water, why did nothing happen to the water? Because water is sodium chloride was ionic compound, and water is covalent compound. Okay, so it's a covalent compound, and covalent compound, I mentioned to you that they share electrons, they don't transfer electrons, and because they share, they can't break apart like that. Okay, when you have ionic compounds and you have a transfer of electrons give and take, those compounds are not held together like this with a bond, they're just associated with each other. So they can go apart, but then they can also come together. Covalent compounds don't break apart, okay, at all. This process, by the way, where you have sodium ions over here and chloride ions here and water all around, this is called hydration. Hydration, because there are water molecules over here. In broader terms, it would be called solvation. Not salvation, solvation. So solvation means that when you have a solvent molecule somewhere, okay? Solvent means that you have something dissolved in something, okay? So let me tell you that also. The two components over here, this is the solute, this is the solvent. And then at the end, you end up getting what's called a solution. Solute is generally a smaller quantity, solvent is the larger quantity. Here, water turns out to be the solvent. If your water was in smaller amount and salt was in large amount, your salt would actually be the solvent, okay? Which, why would anybody use salt as a solvent is beyond me, but, okay? But it's a matter of quantity, that's what I'm trying to say, okay? So it's not that water is always going to be the solvent, no, okay? It depends on what your solution is, okay? So solute is a smaller quantity, solvent is larger quantity, and then you end up getting a solution, okay? So the solvation here is a broader term for when you have a solvent in there, okay? And hydration is very specific when you have water, okay? So far so good, any questions? No? Malika has none, Samara has one.
Okay, so if you had more, say you had more salt than you had water, and the salt like soaked up the water, would it be essentially the same reaction? Like,
It would essentially form a solution.
So, but instead it would be the hydrogen or the water ions don't break apart.
No,
So
never going to.
it would just be pieces of water ions attached to the NaCl.
Again, not water ions, just water molecules.
Water.
These are water molecules, yes.
So it
The
just
only
be water
time,
molecules attached to.
yeah, to each of these,
Okay.
okay? Later on, when you get to GenChem2, you're going to learn a little bit more about this. Okay,
Good.
but right now, yeah, this is
And
it.
in that situation, the NaCl wouldn't break apart, would it? Like if the salt soaked up the water with the NaCl,
It would.
would still be breaking
It
apart?
would still break apart.
Okay.
Yes, so it will still give you sodium and chloride.
Okay.
Okay, just depends on how much water there is, right? So if you have a lot of sodium chloride, but you have only water on one side of it, then you don't have ions here, you only have ions here. Okay, that's what it really means, yeah. The only time that water will break apart, which it does break apart, but it's not like breaking into anything else, and that would be with acid-base reactions. Okay, yeah, that's the only time that water behaves a little bit differently. Okay, but other than that, you will have water only as water. For all these reactions that we do, precipitation, neutralization, oxidation, reduction, if you see aqueous anywhere, that just means water is there. It's not part of the equation. Okay, unless you see it as part of the equation, like here. Okay, then it is a product. Okay, but otherwise, it's just there. Okay, it's just there. We ignore it for most part. Okay, so then my question to you, I don't know if it's the second question, third question, whichever question it is. We have three things over here. Okay, we have three things. We have sodium chloride as in a solid. We have water as in a liquid, and you combine these two to give sodium chloride as in aqueous. Okay, so my question to you is, will these three have different properties? And think about it for 30 seconds before answering. I gotta raise the board also. So will these three things have different properties, and physical properties, not chemical? Okay, so the answer first of all is just yes or no?
Yeah.
Yes.
Okay, fantastic. We're on the right path. Okay, so yes, they should have different properties because they're in different states. Okay, so I will ask you for sodium chloride solid and aqueous. Will they have different properties?
Yes.
Yes.
Yes. Okay, they should have different properties because in one case this is a solid and in one case this is aqueous. Okay, now this is dissolved. In the sodium chloride, were there any ions? There are ions, but it's neutral, right?
Mhm.
Electrically neutral. But when you look at NaCl as aqueous, now you can clearly see the ions in there, right? So now this is going to be a little bit different, okay? And the first part of our chapter here is about electrolytes. And electrolytes are solutions or solvents, whatever it could be, that conduct, anyone? Electricity. So, NaCl solid versus NaCl aqueous, which conducts electricity?
The liquid.
The liquid, not the liquid. Aqueous.
Oh, liquid.
Aqueous. Okay, all right. Aqueous conducts electricity. Is everybody nodding their heads? Yes? And you're very true. Okay, the aqueous will conduct electricity because it has the ions. NaCl also has the ions, but those ions are actually held together. Okay, they are tightly bound. They have no space to move, so they cannot conduct electricity. When you have power going on in these lines over here, that's because the electrons are in motion. Okay, they're carrying the electricity with it. So in this case where you have a solid structure, again, I can bring up my crystal structure from here. Everything is held tightly in place. Okay, so it will not conduct electricity. By the way, just as a little information for you, if I were to turn the sodium chloride into liquid, not aqueous now, liquid, will it conduct electricity? Yes, it should. Okay, because suddenly now it has that free flowing of electrons possible in there. Okay, so you can change the properties of any substance. Okay, by changing this the state of a substance. So here we change it from solid to aqueous. Now my question to you is about water. Water is a liquid by itself. Does it conduct electricity?
Yes.
Well, if you can get electrocuted, so that would.
So yes, it does, right?
Yeah.
Okay. Depends on the type of water. So do you want to clarify that? Then tap water, very good, because salt water
Has the ion.
has maybe more ions in it. Okay, so yeah, you're on the right track there. Okay, what about water as in just pure H2O?
Like in what form?
Yeah, something like that. It is in pure H2O. There's nothing in it. Nothing in it except for water. Just H2O. Does not conduct electricity. Okay, so pure water, which is just H2O, liquid, okay? The problem is that we don't encounter such waters.
Yeah.
Okay, that's our problem, okay? And that's why sometimes we don't know the answer to this, because the water that we encounter is usually tap water, seawater, dirty water, rainwater. All of these waters, they all have something dissolved in it, okay? And bottled water companies, if they ever tell you this is the purest water possible, forget it, okay? That is not possible. Next week, I'm going to show you how that works, okay? Not today, because I have to bring my whole shebang thing with me. But yeah, but otherwise you can clearly tell, okay? And so please, next time you come, do bring those water bottles with you, okay? The more variety we have, the better it will be for us. But you can test the water and tell whether it's pure or not just by testing it. Because if it is an electrolyte, then it has ions in it, right? And if it has ions, it conducts electricity, which means that you should be able to light the bulb, right? Okay, so that's what we're going to try and do. H2O by itself, pure water, should not have any electrical current in it. Okay, and actually, that's how I found out that some of our distilled water was not distilled water. Okay, because it was conducting electricity. It should not be conducting electricicity. But anyhow, it happened. Okay, so what do you do? There are two kinds of water that we talk about in labs usually. One is deionized water, one is distilled water. Okay, distilled water generally is when you boil the water and you condense the vapor that comes out. That's distillation. And technically speaking, the vapor that comes out that you condense is supposed to be the purest form of water also. Yes?
But can the purest form, can it only be in a vapor?
Yes.
Because if it touches anything else, then it automatically has other ions in it.
Exactly. So that's why it depends. So the vapor that you form in the atmosphere is not the purest form, because the atmosphere has all sorts of other things in it. But when you're distilling water in a lab, then it's a closed environment.
But even if it's in a glass, like anything on the sides of the glass could get in the
So
water.
hopefully
anyway.
you have clean glassware. I hope in a lab we have clean glassware.
But
The other type of water that you have is what we call deionized water. Deionized water means that all the ions have been taken out. Okay, so depending on which lab you work in, like our GenChem labs usually don't require deionized water. Okay, because we're not doing any kind of hi-fi chemistry. Okay, we're doing just normal type of chemistry, and you can work with distilled water. But in biochemistry and stuff where you really need pure water, okay, or electrochemistry for that matter, you would need deionized water. So you want to make sure there are absolutely no ions in there. So there is a different process for that where you remove all the ions, okay, and that would be more pure aqua
so
water.
distilled water and deionized water are not the same
The
thing.
processes are not the same. Okay, the processes are not the same for both. Ideally speaking, the product should be the same, because the vapor water that you have, the steam that you end up getting, should be pure, provided all your other glassware is clean. You're really worried about your glassware, aren't you?
Well, I mean, even like, because the distilled water in the lab is in a plastic bottle.
Yeah.
And how are you to be
And
sure
what is
that that
plastic?
plastic is
And
not?
what is that plastic? Is that organic? Is that covalent, or is that ionic compound?
An ionic compound.
Hmm?
It's ionic.
How is it
No,
ionic?
it's-
If it was ionic,
No, it's-
don't you think it would
It
dissolve?
would dissolve, okay.
Okay, all right.
So
Very
if it's
good.
if the if the
We're having fun
distilled
now.
water is in something that's a covalent bond, it will stay distilled as long as there's nothing inside.
So as you learn more chemistry, you will learn about solubility of molecules a little bit more when you get to GenChem 2, and then you can have a little bit more idea, okay, about how you can figure out what kind of solvents should be kept in what kind of bottles. Because yes, we are very careful of that in our chemistry labs, because your concern is our concern, exactly, okay? That you don't want any contamination in there, okay? But that is something you learn as you go on, okay? Not everything can be answered right here, okay? But you answered correctly though, for most part, that this is not an electrolyte, this is an electrolyte, and technically pure water should not be an electrolyte. Okay, but the water that you encounter for most part is an electrolyte because it's not pure water. Okay, tap water has ions in it, all sorts of water has ions in it.